start with the next session. We are very happy to have Godfrey tell us about augmented batch exchanges.
Thank you very much. So I'm going to tell you about augmenting batch exchanges with constant function market makers. And this is joint work with my co-authors and my advisors as well at Stanford. So what's the problem? Well, there are two ideas that have been around for a while in market design that have gotten a lot of prominence and attention in recent years, especially in the blockchain space. These are operating exchanges as in a batch model, and also these constant function market makers, which we just heard about. So what we'd like to do in this talk is think about what happens when we stick them together. And this is not just an abstract mathematical question that I cooked up for my own amusement. This is something that happens in practice. And in fact, different implementations have made different choices with different qualitative results. So we'd like to understand these results. It turns out there's no optimal way. And so we really need to think about the different trade-offs. So just to recap, we're going to think about a model where there's, say, n different assets, and these are all regular, divisible, fungible, say, tokens. And users are trading through things like through regular limit orders. Things like sell some number of units of one asset for at least some number of units of another asset. And we're going to assume that users always prefer to receive more of what they're buying than less. Now, the regular way you do this is just with a collection of central limit order books running continuous double auctions. And you'd have, say, n squared different trading pairs, or somewhere between O of n and n squared. The batch model is different. Instead of processing trades sequentially, you process a whole collection of trades all at once. So the batch is, say, this is not a pointer. Okay. The batch is given a whole bunch of input offers to trade, and then the batch, we'll call it a pricing engine, looks at this set of offers and computes a price for every asset. The units here don't really matter. What matters are the quotients. Given these quotients, every offer checks to see is the offered price by the batch greater than my limit price. If it is, it trades. Otherwise, it doesn't. And I just want to point out, this is not pairwise matching. This is a sort of in this example, at least, there's no pair of these offers that's able to trade, and yet we're able to make a bunch of trades here. We'll say that the set of prices clears the market if, after this whole process, the batch itself has no surplus or debt of any asset. I'll get to where these prices come from, but why is this nice, especially in the blockchain setting? Well, once we have these prices, all the rest of the work of running an exchange is effectively parallelizable. So you can actually implement this efficiently in practice, subject to, and it turns out that both asymptotically and empirically, you can actually compute these prices efficiently. On the economic side, if everyone in a batch gets the same prices, then you eliminate a common class of front running that's especially prevalent in decentralized exchanges. I can't reorder trades for my own benefit, essentially. You also eliminate this cyclic arbitrage problem, which is common in decentralized exchanges, where, for example, I start with some amount of assets, I make a bunch of trades, and I wind up with strictly more of my assets than I started with. The way this works under the hood is that it's running the what's called the Erro-de-Bro exchange market model. This is a classic model from the econ literature. I'm sure most people have seen this before. We're going with the simple version of the model, where you can think of it like a game. There's some market player that chooses these prices, and then every agent in the market picks some trade that maximizes their utility, subject to the budget constraint, where the budget is determined by the market prices. Closing the loop here, each of these regular trades corresponds to an agent in the market with a linear utility function. Agents have utility for what they're buying and what they're selling. Now, in this, it's not true that this market always has an equilibrium or that the equilibrium is unique. But in this narrow class of markets that we're considering that have these utilities, there's always exists an equilibrium, and this equilibrium is sort of unique up to rescaling prices. It's not strictly unique, but all equilibria share the same price vector. The nice thing about this is that, one, we have this nice mathematical framework that we can work with. And two, if we're running this in practice, because of this sort of uniqueness or unique star property, whoever's running the batch doesn't have to make strategic decisions. They just have to compute some fundamental mathematical property of the batch. So what's the other thing? Well, that's the constant function market maker. This is some market making tool that's parameterized by a set of reserves and a trading function. Generally speaking, what I plotted here is some XY plot where some point in this graph is like an amount of assets X and Y. And the CFFM will accept a trade from like one point to another if and only if this doesn't decrease the value of the function. We're going with this doesn't decrease criterion instead of a strictly equal criterion because this is actually what's checked in practice. So just as a definition, we're gonna say that the spot price of the CFFM is the sort of the marginal the exchange rate offered by the CFFM for a trade of infinitesimal size. This is essentially the slope of this curve. Now, why do people do this? Well, we need some way of adding liquidity to a market, and this is an efficient or sort of computationally simple way of doing that. So as I said, there's several projects out there that try and combine batch exchanges with constant function market makers. And they all do it in slightly different ways. So our goal with this talk is to figure out what are the qualitative trade-offs between these different ways of integrating CFFMs into batch exchanges. Great. Again, our model is there's n assets, there's one batch exchange, and in that batch exchange, there could be many different limit orders, and there could be many different constant function market makers. Each of these constant function market makers could have different curves, different sets of reserves, and sort of just be arbitrary. What's not captured by the model is that there's also, this exists in a context. And so there's also things like Binance and things like other exchanges that we might want to think about. And that affects the kind of design choices we might like to make down the road. Great. So at a basic level, what properties do we need from some combined system? Well, we can't mint money out of thin air. That's sort of the basic. We'd also like to maintain this uniform price property. That is what gave us these like nice fairness and combating front running properties. We'd also like to ensure that your limit sell orders sort of behave as you'd expect. They should, if you offer someone a high price, they should take that high price and not just settle for a slightly lower price. These are just standard market design assumptions, and these sort of, informally speaking, sort of categorize the nice things about the arrow-to-grow exchange market. And on the side of the constant function market makers, well, all we know is that we don't want the constant function to go down. But now we've really messed up our model, right? Now, all we've said is that the CFFM has to trade to some point in this gray region, right? We can't go below this the blue line, the blue curve, and we can't trade it better than the batch prices. And so we now have this big space to choose from. On the one hand, so the big consequence of this is that the market equilibrium is not unique anymore. This also just messes up our mathematical framework that we had and complicates the problem of actually computing equilibria. So what should we do? How should the CFFM choose a batch, choose a trade in a batch? Well, if you think of, first of all, there's some things that you might naturally think of as like reasonable. You could think about trading, say, all the way across. That's to say point B. You could think about, this constant function is defined everywhere. You might think of that like a utility function and try and maximize that. That gets you to point C. You could also trade along the curve until the spot price equals the batch price. Sounds reasonable. The first thing you might notice is that if you have just these basic axioms, you can't actually trade along the curve. You have to trade along at the batch prices along the orange line. Otherwise, some asset is not conserved. Great. Some other things you might want. You might think that you want the batch equilibrium to be Pareto optimal. Here we have, we're taking the point of Pareto optimality from the perspective of the traders, not from the CFFMs. We don't really have a utility function for the CFFMs yet. And I'll just point out that, in the regular batch model, before we added the CFFMs, we didn't have to worry about Pareto optimality. Everything was Pareto optimal. It's only when we add this extra flexibility that we make our life harder. We might also like to have the CFFMs after the batch be left in what we'll call a price coherent state. At a high level, this is just requiring that after the batch, there's no like free money left on the table. There's no way that I can start with some asset, make a bunch of trades, and wind up with strictly more of the asset than I started with. You might also weaken this to say that we'll stay with price coherence, but only if we started in a price coherent state. It turns out these are incompatible. And so no mechanism, no way of doing this can actually get both. The proof intuition is basically just that you might have multiple CFFMs trading in a batch in the same asset pair. And if you want to get Pareto optimality, you can construct examples where you have to trade all the way across. And if you have different curves, then the slope of the line at this intersection point is going to be different for different curves, and there's nothing you can do about that. So, okay, we can't get both. What else might we think about getting? Well, you might like the CFFMs to learn something about the price of the assets in the batch. You might say that the spot price of the CFFM should be equal to the batch price after the batch. That sort of implies that you have to trade to this point C on the graph. But I want to point this out because this gives an example of how the context in which you deploy these things matters. In some batch exchanges, a user can come along at any time and initiate a batch whenever they want. And in some implementations, these happen on like a fixed frequency. In some implementations, there's a lot of limit orders in a batch, and in some, there are sort of very few, maybe one or two. And if there's a lot of limit orders and batches happen at a fixed frequency, then trading to C is probably fine. But if users can initiate a batch whenever they want, and there's very few users in a batch, then trading to C actually incentivizes a user to split their trades into 1,000 or thousands of tiny pieces, which sort of effectively winds up in net trading to point A. This is going to give worse performance for the market makers, and maybe this is a problem. Another thing you might want is for the rules to be predictable and sort of computable as a function of just the CFFM. I'll get to why this is nice, but once we have this, some things to point out is that, well, if you want price coherence, the only thing you can do is trade to point C. But in fact, also, if you want preservation of price coherence, there's a big class of things, of rules of points that you can do. But in particular, what's interesting is that, in fact, trading all the way across to point B can be made to be price coherent, but only if all the CFFMs use this constant product curve. This is what Uniswap and others choose. This turns out just the constant product curve has a lot of nice symmetry that you can work with. So why do we want this local computability, or why is that nice? Well, let's think back to how this question of operating a batch exchange. Somebody has to compute a batch solution or equilibrium. And the simplest way to do this is, of course, write out the whole thing as some optimization problem, throw it at Gurobi, and wait for a long time. This is not really scalable. We'd like to come back to this mathematical framework that we had. And local computability does exactly that. Essentially, if something is locally computable, then there's a whole class of algorithms from the literature based on auctions and iterations that you can just apply directly to the system without making any modifications to the algorithms. That's pretty nice. You need a couple of regularity conditions. You need the rule to satisfy what's called weak growth substitutability. This is just saying that if the price of a good goes up, the demand for it doesn't also go up. This is a fairly standard condition in the literature on this topic. So I'm going to tell. So this is probably fine in practice, but I'm going to point out today that these there's actually some extra structure here that we can play with, and I'm going to point to a convex program for this kind of a problem. So the key idea is that most CFFMs don't trade between an arbitrary number of assets; they trade between two assets. And if you have a CFFM that trades between two assets using some locally computable rule, again, that satisfies our regularity condition, then in fact, it's sort of in aggregate acting equivalently in some sense to an uncountably infinite continuum of regular limit sell orders. So what we can do is essentially adapt a convex program for the linear case of Arrow-Debreu exchange markets to this sort of infinite case. Don't try and parse this program too much. It's not intuitive. I just want to point out this is the convex program for the linear case from Devon Goguen Bay. And you see the objective, it's just a summation over a finite set. Once we switch it to our setting, we swap the finite summation to a bunch of integrals. And there's some other shenanigans to play. But the main idea is still the same. And I'll just point out this, this objective, you can compute it. If your locally computable rules and trading functions are like, computationally simple, then you can actually evaluate this, compute derivatives, solve it in practice. And I'll point out that, I framed this in the context of CFFMs, but in fact, what this is doing is solving the case of exchange markets, where every agent in the market is interested in only two assets. There are many assets in the market, but each agent is interested in only two. But subject to that constraint, the agent is allowed to have any utility function satisfying weak growth substitutability. This is a class of utility functions that it seems to show up in practice, right? This is the curves that most CFFMs use. It's also fairly expressive. There's a wide class of functions that satisfy this, and it seems to be analytically tractable. And so I think this is sort of an interesting subclass of utility functions to maybe study some more. Surprising to me, this hasn't showed up more in the literature. So just to wrap up, what have we done? Well, we have these two mechanisms for integrating, for trading in decentralized exchanges. We have batch exchanges and we have constant function market makers. And we've explored, we've given a basic set of axioms that we'd like to preserve when you stick them together, and shown that subject to those axioms, a bunch of natural desiderata that you'd like to get out of the combined system are actually incompatible. And so if you want to deploy these in practice, it's really important to think about which things do I care about, which things do I not care about, and how does this fit into the broader context of my system. If we want to actually run these things in practice, we need to be able to compute equilibria efficiently. For that, it's really nice if the trading rules are locally computable. And subject to that, you can get, for many classes of utility functions, a nice convex program that's actually tractable. Thank you very much.
Perfect. Questions? Oh. Maybe I ask a question if they're not. So if I wanted to implement this on the blockchain, would I solve this convex program on the blockchain, or how would I do this?
Generally, the way is that you have some off-chain system that solves an equilibrium. It's very easy to generally check that something is an equilibrium, then much harder to solve, right? To check it, you just have to execute a bunch of trades and check that everything adds up to zero. Okay. So generally, the way this works is that somebody off-chain solves it and then posts the solution on-chain.
Yeah, so I'm sorry, but I kind of missed the framework here. So maybe I could just try to rephrase what I think is happening, and you can correct me when I'm wrong. But so this would be like an idea where Uniswap would build a batch into their, like a batch system into their router and say, okay, at any point in time, you can, sign up to be routed through this batch process, and we're going to determine, how the trades get settled at the respective liquidity pools. Or is it or am I totally off on that?
That's one way that one could run it. I think what's particular about the batch model is that if I signed up to that, my trade wouldn't get routed just on its own. It might get routed. There might be like several people simultaneously sending trades, and we'd all get routed together.
And I can choose to bypass this, or this would be like you have to go through the batch router. Like in your models.
So we're sort of agnostic to that. So I think there's some chains where everything goes to the batch, and then if you try and do this on Ethereum, of course, you can do sort of whatever you want.
Thanks.
Hi, I'm curious if you've had an opportunity to empirically test this algorithm against the aggregators that are out there. Like 1inch was mentioned, Paraswap, Uniswap's working on a product.
Testing like this sort of batch model empirically is, I think, a very interesting open problem. And the real challenge here is that anytime you change the way that like the mechanism for how people trade, that changes their incentives, and then this changes the way they interact, right? So it's not really clear that you could just take regular trading data and apply it to this model. To get it, like you'd have some sort of apples to oranges comparison. But I think figuring out how to do that would be very interesting. But no, I haven't done that.
Thank you.